Welcome to the Deep Dive. Today we're jumping into something pretty fascinating, the 2025 Nobel Prize in Chemistry. It went to Susumu Kitagawa, Richard Robson, and Omar Yagi for developing metal organic frameworks, MOFs for short. Our goal today is to unpack what these things are and why they're causing such a stir, changing fields from energy to medicine.
It really is a huge moment for materials science, a defining moment, you could say. They essentially created a whole new way to build things at the molecular level. The Nobel Committee called it creating rooms for chemistry, which I think captures it perfectly.
Rooms for chemistry? Okay, I like that. So for someone new to this, what exactly is an MOF? Lay it out for us.
Right. So imagine tiny, tiny crystal sponges. That's sort of the idea. They're crystalline polymers, very porous. The formal name is reticular materials, which just points to that net-like structure they have. And they're made from two main bits. Inorganic metal clusters, we call those secondary building units, or SBUs. Think of them as like the corners. And then you have organic molecules acting as the struts or linkers connecting those corners. The really neat part is how they lock together. They form these crystal structures with really big, stable, empty cavities inside.
Okay, so stable empty space is the key.
Yeah.
And this all falls under something called reticular chemistry, right? From the Latin for small net.
Exactly. That's the field focused on designing and building these network structures.
So where did this whole idea start, building these molecular nets?
Well, the first real steps were back in 1989. Richard Robson, he managed to build these first four-arm constructions. They looked ordered, sure, but they weren't really stable. The problem was you remove the solvent they were made in, and poof, the whole structure often just collapsed.
Ah, right. Not for useful then.
Not really. It was Omar Yagi who cracked that stability problem. He introduced the SBU concept, those rigid metal cornerstones I mentioned. That led to MOF5 back in 1999, and that was the breakthrough, the first one that showed, ultra-high porosity that stayed porous permanently.
Okay, so Yagi brought the stability. Where does Susumu Kitagawa come into the picture?
Kitagawa's work was crucial too. He showed pretty quickly that gases could actually flow easily in and out of these MOF structures, and importantly, he predicted they could be flexible, that the pores themselves might sort of breathe or change shape depending on what gas molecules were inside.
Interesting. So stability from Yagi, dynamic behavior from Kitagawa. But what makes MOF so different from, say, zeolites, the older porous materials? Is it really just about control?
It's absolutely about control and the level of control. We're not just finding materials with holes anymore. We're designing the holes, atom by atom, almost. You get to pick your metal SBU, pick your organic linker, and these linkers can often connect in multiple directions. They're polytopic. This gives you a massive, almost infinite design space. We call it tunability. We can tailor the size, the shape, even the chemical environment inside that cavity.
Okay, designing atom by atom sounds amazing, but how do you actually make these things practical, not just tiny lab crystals?
Yeah, that's key. The standard way is often slow solvothermal synthesis, growing crystals over time. But for scaling up, people now use faster methods. Things like microwave-assisted synthesis can speed it up a lot, and critically, you can even tweak the MOF after it's made. Post-synthetic modification, we call it. You can swap out metals or linkers to fine-tune the properties.
The control makes them sound perfect for catalysis. You mentioned they have advantages over zeolites there. Why is having bigger custom pores so important?
Well, zeolites are great, don't get me wrong, but their pore structures are pretty fixed. MOFs give you more options, different coordination geometries around the metal sites, and yeah, pores often much larger than 1 nanometer. This is really vital for complex reactions, especially something called asymmetric catalysis.
Asymmetric catalysis, why is that a big deal?
It's huge, especially in pharmaceuticals. Many drug molecules come in two mirror image forms, like your left and right hands. Often only one form works, and the other might be useless or even harmful. Asymmetric catalysis lets you selectively make just the one specific mirror image you need. And MOFs, with their tunable chiral environments, are proving really good at that.
Okay, that makes sense. Vital for safe medicines.
Yeah.
Let's switch gears slightly to some other big applications that might impact listeners directly. Where are MOFs making waves right now?
Oh, several areas. Environmental cleanup is one. Energy storage is another big one. For storage, think hydrogen fuel. MOFs like MOF 177 show really high hydrogen capacity. And the storage mechanism is often physisorption. It's like a weak physical attraction, not a strong chemical bond.
Physisorption, like static cling.
Exactly like static cling. It holds the gas gently. This means it's reversible, and you don't need high pressure or temperature to get the hydrogen back out. That makes it potentially safer and more efficient for things like fuel cells.
Safer and more efficient. Sounds good. What about pollution or water issues?
Definitely. For carbon capture, some MOFs, like MEG.DC, are really effective at soaking up CO2. Others can break down persistent pollutants in water, maybe pharmaceuticals that get into rivers, or even separate those nasty PFAS chemicals. And for water itself, MOFs like ZIF8 and UIO66 are being explored for desalination, removing salt. There's even research on using MOFs to literally pull water vapor out of dry desert air, harvesting water from the atmosphere.
Wow, from capturing carbon to harvesting water from air, that's quite a range. And you mentioned medicine earlier, too, beyond catalysis, like
Mm-hmm.
delivering drugs.
Yes, exactly. Biocompatible MOFs, like one called CDMOF1, have been used to encapsulate drugs like ibuprofen. The porous structure holds the drug, potentially releasing it more effectively in the body. So the value really is in making these custom materials for specific jobs.
Tailor-made chemical tools, basically.
Yeah.
Okay, so looking ahead, what's the next frontier?
Well, something really exciting is their electronic properties.
Mhm.
Because those organic linkers are, organic molecules, MOFs naturally behave like semiconductors or insulators. And what researchers have figured out is that by changing the linker, you can actually tune the electronic band gap. That's the energy needed to get electrons moving. They can tune it across a really wide range, maybe 1.0 to 5.5 electron volts.
So, wait, you start with designing chemical sponges for storing gas.
Yeah.
You end up potentially designing electronic materials, too.
Precisely. That ability to engineer both the chemical function and the electronic properties in one material, that opens up huge possibilities. Think about future optoelectronic devices, things involving light and electricity. MOFs could play a massive role there.
Custom chemistry meets custom electronics. Definitely something to think about next time you hear about new materials in energy or computing. It seems MOFs are just getting started.